Hi everyone, I am Dr. Srinivasa Gupta, Professor, Department of Mechanical Engineering, JYOTHI Institute of Engineering and Technology. As part of Dynamics of Machinery lectures, today we are going to discuss the important concept on brakes and dynamometers. We will see what is a brake. Basically, brakes, we can say there are different categories: mechanical brakes, hydraulic brakes, pneumatic brakes, all these. We are basically talking about mechanical brakes. What is a brake and what is dynamometer? What is the difference between these two? We are going to see. First of all, a brake is a device by means of which artificial frictional resistance is applied to a moving vehicle or machine member or material handling crane or hoist, anything, in order to, what is our purpose? To retard or make it slow or stop the motion of that particular machine or vehicle or material handling, crane, hook or anything. In the process of performing this function, what happened? The brake absorbs kinetic energy because a moving element has kinetic energy. If it is bringing down from height, like material handling equipment, in that case, the potential energy given up by that system, the purpose of that is to bring lower, make it down the objects, that is objects being lowered by hoists or elevators. That is the brake. Brake is a device which is used to retard or stop the motion of machine or vehicle or any material handling device. But a dynamometer is basically a brake, but in addition it has a device to measure the frictional resistance. How much frictional resistance need to stop or make it slow down or retard the motion. That also we can measure using dynamometer. The additional function of dynamometer is knowing the frictional resistance so that we can obtain the torque transmitted and power of the engine also from this. Coming to types of brakes, mechanical brakes, basically all these are shoe brake or block brake, we can say, and pivoted block or shoe brake or double block or shoe brake. Number of blocks are more. That's all simply. And band brakes. In band brakes, simple band brake, differential band brake. And there is a combination of these two, band and block. And the other one is internal expanding brakes. Today we are going to discuss about basic concept on single block or shoe brake, the analysis part of it. Okay, single block or shoe brake, we can see in the diagram. Basically, it consists of a shoe which is attached to the lever. Let us take a lever, all of you. Lever is this one, let us say lever having some length L. So, a block is attached to the lever, fixed firmly. Then, it is while applying the brake, by applying some force, let us say some effort, this is. Then, on the rotating drum, because vehicle or any system has a rotating element, that is we can say rotating wheel or drum, if it is rotating in some direction clockwise, let us say. Then if you apply the effort or make it contact the shoe with the rotating drum, then there will be a force or we are exerting a pressure on the rotating drum against the rotation, then there will be a retarding the motion or stopping the motion of the wheel. So let us say the applied force P we are applying at the end of the lever. Lever is pivoted at the other end, let us say pivoted, and we are applying this force. How the wheel is going to be stopped? Because of frictional force between this block or shoe, we can say, and this wheel. So we can say any two members having a friction, there will be a normal force pressing the brake block on the wheel. So this normal force. So for this we need to understand free body diagram. I am taking this lever. You are able to understand this is wheel. Okay, this is lever. First of all, you need to understand the terms and effort applied, that is P, let us say, and length of the lever is L, and radius of the brake drum or wheel is, let us say, R, and suppose it is rotating clockwise. Okay, then take the free body, this is the shoe, okay, or block, which is attached firmly to the lever. Okay, we can also see that the distance between center of the shoe and lever arm, that means effort we are going to apply. This is, let us say, L2, and distance from pivot to center of this shoe, that is L1, like that. Total length is L. Okay, so I am going to take free body diagram of lever with the shoe because this is one part. Then if wheel is rotating clockwise, what is the direction of frictional force? Obviously it is on the wheel. Wheel is rotating clockwise. On the wheel surface, the frictional force is opposite to the direction of rotation. This is frictional force. Okay, let me say, because it is tangent to this surface, I can say Ft. Then if you take block, the frictional force, obviously it is in opposite direction. Are you able to understand? These two, when they are joined, then this is cannot be shown as it is constraint force as we studied before also. Okay, the P is load, P is load applied here. Okay, now how we can analyze? And also we can define R 2 theta, angle okay, of contact surface, this angle block with the wheel is, let us say, 2 theta, this angle. Okay, so these are the terminology. Rn is normal force. If you take free body diagram, there is a frictional force and there is a normal force Rn, normal reaction we can say. On the drum we can say reaction, normal reaction we can write. Okay, are you able to understand? I think. Okay, now these are the forces on free body diagram we can show. Okay, this is fixed lever part. Okay, or we can say there are reactions if it is not fixed, right? Now coming to the, okay, this block is made of softer material than the rim always, because if at all replacement is required, we can replace the okay, this shoe or brake, it is less cost. Okay, this type of brake is basically used in railway trains and tram cars. Because of friction between the block and wheel causes the tangential braking force to act on the wheel, which retard the motion obviously. So the block is pressed against the wheel by a force applied on one end of the lever, that is, I said, effort. So block is rigidly fixed to the lever, so entire lever is pressing with the block on the wheel. Okay, so the lever is fixed at the fulcrum, that is at O. I will show you where the diagram. Okay, O, this is the O. Okay, so now coming to the analysis part. So as we know that mu is coefficient of friction between the wheel and block, and Ft tangential braking force at the contact surface. If the angle subtended by the shoe on the wheel is 2 theta is less than 60, then we can assume it as normal pressure exerting on the block or on the wheel is uniform. In such cases, we can write Ft is mu Rn. As you know that friction force is coefficient of friction times normal reaction. Okay, let us now consider the case 1. Case 1 is, what is that? When the line of action of tangential force, the tangential braking force passes through the fulcrum. It has been, okay, I will draw here. Okay, this is the fulcrum lever, this is the fulcrum. Okay, the tangential force, okay, on this we have shown the direction because rotating clockwise, brake drum is rotating clockwise. So the tangential force direction is on the shoe is Ft. This is mu n. If it line of action of this tangential force is passing through the fulcrum, that is in line, coincide with the line of action. This tangential force as well as fulcrum, that is passing through the fulcrum. Then we can write, then that is first case. So in that case, we will have take the moments about O. What are the forces on this lever? P effort, Fn is this one, Rn, okay, normal reaction. Now taking the moments about fulcrum O, then moments about O, which is going to give this, let us say this distance, I already mentioned, this is L1 and L2, okay, or you because this distance is based on the requirement of the effort, we can vary. That's why here let us use X. If that is vary, then L2 also vary. Total length is X plus L2, L of lever length. Okay, then we can write, taking moments about fulcrum, then we can write Rn into X. Okay, this is anti-clockwise direction, minus P into L. Okay, clockwise direction moment. Okay, this we are going to, these are the forces Rn and P, because Ft is line of action Ft passing through O, that moment of Ft about O is 0, as you know. So this must be 0 to maintain equilibrium. Then we have Rn equal to PL by X. So what is the normal reaction required? Based on that X we can vary. So and also this is normal reaction. Braking torque I want. Braking torque, how can we estimate? Braking torque is equal to frictional force into R, radius of the wheel. Then frictional force is obviously mu Rn and into R. Okay. So this is, we know that mu into Rn is PL by X. Okay, effort we are applying, because in terms of effort only we know, Rn directly we cannot measure. That's why we are writing like this. So this is braking torque. That means the total torque with which we can stop the wheel is required is this much. Okay, mu PL by LR by X. Okay, you know the each variable definition of each variable. Okay, how they are defined. Then case 2, let us take that line of action of course, if you want to see if the wheel is rotating anti-clockwise, in that case also you will get same relation for braking torque. You can verify by doing this. Similarly, case 2, and the line of action of this tangential force, the braking force is not passing through the pivot point, but it is some, let us take, it is lying a distance. Okay, this is tangential force in the clockwise rotation of the wheel. Then it is lying a distance, this is O, let us say. Then this distance, parallel distance is perpendicular distance. If you draw line of action here at O of same line of action as Ft, then this is A, let us say. Okay, effort is P. Okay, then normal reaction Rn. Okay, it is all block or shoe free body diagram, because shoe is attached lever along with the lever. In this case, if you take moments about fulcrum, then you are going to get Rn equal to PL by X plus mu A. Okay, so it is clockwise rotation. So, but if drum is going to rotate, wheel is going to rotate anti-clockwise, then you will get Rn is PL by X minus mu A. You can check it. Okay, so what is the difference? That means frictional torque required, braking torque required is mu Rn, that is tangential force into R, as you know that. So here either normal reaction or frictional torque required, which one, in which case it is more. The, means if drum is going to rotate clockwise, wheel is going to rotate clockwise, the frictional torque required is frictional torque existing. Torque on the drum is you see in the denominator x plus mu a. So means it is less than the frictional torque required to stop the wheel in the case of if wheel is rotating anti-clockwise. As you observe this, see here, okay, less in case of frictional torque, less in case of second case anti-clockwise rotation, drum is rotating. So means less torque is required to stop the wheel. Why? Because you can see the moment of tangential force about fulcrum is opposite direction than the effort we are applying, moment of effort about the fulcrum. Means frictional force which is not doing favor to the braking process. Okay, in first case, if wheel is rotating clockwise. If it is rotating anti-clockwise, we need less torque only. Means we can understand in this case, okay, the FT, line of action of FT is just above the, okay, I will draw here. Line of action of FT is, okay, this is the pivot, this is the FT. Okay, see, line of action of FT is distance, let us say B, above the A, okay, above the fulcrum. So in this case, the effort applied, okay, moment of effort about fulcrum and also the moment of frictional force about fulcrum are in the same direction. Because of that, it is supporting the friction grip, pressing, more pressing occur on the wheel, and less effort is enough to apply required torque on the wheel. I think you are able to understand this point. This is most important. So the which direction is rotating and the pivot, especially where we need to locate the pivot point on the lever, that is important point here. So less effort only we can stop the motion of the wheel. That means we can apply the brake. Okay. So in one more case also we can see, if that is the third case, as I mentioned, x minus mu a. Okay, that is if lever pivot point of lever is okay just below the friction tangential force on the tangential force or frictional force. Okay, I think you are able to understand this point. Now we are going to take this is one when the brake wheel. Okay, this is about all this. Then let us take a simple problem. We will see. Suppose this is single block brake is applied applied to a drum. Drum radius is given, rotating at 250 rpm. See that means drum radius is 0.35. It is rotating at 2500 sorry 250 rpm. 250 rpm. Okay, then the normal force exerted on the block Rn is 2500 newtons. The coefficient of friction between block and drum is 0.32. Okay, we need to calculate braking torque. Braking torque we know that, okay, mu Rn into R. Okay, we can substitute mu is given 0.32, Rn is 2500 and R is 0.35. We will get the braking torque. Okay, but frictional power, how much power absorbed by the brake? That power is, we can calculate torque times angular velocity. As you know, 2 pi nt by 60 power, okay, absorbed. So this omega is 2 pi n by 60, that is 250 rpm is given n. So omega you can calculate 2 pi n 250 by 60. Okay, you can calculate power, frictional power absorbed by the brake also. So these are the values. You will get tangential or frictional force is equal to 800 newtons, and you will get torque, frictional torque needed is 280 newton meter, and this omega angular velocity in radians per second is 26.18. If you substitute relevant values in the relation, then frictional power needed to stop the brake is this one, 7.33 kilowatts. This is about simple, very simple problem. Then coming to the another problem, that is some unknowns. Normal reaction between shoe and drum is unknown. Suppose the force applied at the end of the lever, how much effort is required, and power absorbed by the brake, of course, that is as usual. In that case, you have to use a relevant relation and substitute the values. Here in this case, a single block brake is applied, drum radius is given R, okay, and it is rotating at 300 rpm. So omega is 2 pi and n is given 300 rpm. The coefficient of friction mu is given 0.3, and the brake lever is 600 mm long. Total length of the lever is 600 mm long from pivot to effort point. Okay, the distance from fulcrum to the point where the shoe presses is 100 mm given. Here in this case, L1 is 0.1 meters or 100 mm. Okay, L1 is 100 mm, total 600 mm, L1 100 mm. Obviously, L2 is the braking, okay, L2 is remaining, you know that. Okay, then the braking torque required is, braking torque given here directly, braking torque 600 Newton meter given. Then you need to determine normal reaction. So, for this, it is better to draw the configuration diagram. Whatever case you are going to assume, here particular case is not mentioned, pivot is above, below the frictional, okay. So each case you have to verify, okay. This is Ft, frictional force, and Rn, and this distance is given, total is 600, and this is 100 given. Of course, this is, you know that, 500, okay, this is 500. Then this is pivot point. Here, suppose you take, this is aligning with the line of action of frictional torque, frictional force is passing through the pivot point. In that case, you write the relation and try to find unknown normal reaction required. Because if you write this one, frictional torque required, mu Rn into R. Okay, because this frictional torque required is given, then okay, braking torque is given, then mu is also given, Rn is unknown, R is given. So directly you can substitute and you can find. Second one is the force applied at the end of the lever. Okay, so in this case you have to take moments about this, and P into L, you can write the relation, P into L is okay equal to, you can directly Rn into, in this case, Rn into 100. So what is this force applied at the end of the lever? P you can calculate in this. Other cases, if pivot point is below the frictional force or pivot point is above frictional force, those cases also we can write relevant relation, take moments about O and write the relation and substitute, you can get effort required. And power, obviously if you frictional torque is no, power is, you can calculate, this is frictional torque into omega. Okay, braking torque into omega, power required. Okay, you can use and you can solve this problem. Okay, this is all about this, very simple, and we will see in the coming next class. We will see other types of brakes, band brakes, okay, double shoe brake, okay, how we can solve analyze the braking system. With this, I am concluding this lecture here. Okay, thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.